And so today I'll share about our work on towards this vision of building like a virtual AI biomedical scientist that can automate all kinds of research tasks for specifically for the biomedical field. So I would probably spend around 5 minutes to give a kind of quick intro, like why do we care about this problem and why are we working on this? And then I'll spend around like maybe another 10 minutes talk about our method and then also delve into the result for another 15 minutes. And then I can do a 5 minutes of quick demo as well, just to let people feel the exact what is going on. And then maybe we have 20 minutes for question and answering. Um, Cool. So just to kick off the motivation, as everyone probably all know, like biomedical research is a very fundamental across numerous industries. So moving beyond drug discovery, there's also clinical diagnosis, like even like agriculture, consumer health, like this continuous glucose monitoring, and manufacturing and skincare and so on and so on. And what we kind of think a lot about this direction is like based on this observation, that is like we realize that biomedical progress is partially limited by lack of ideas, but another big reason is just limited by human bandwidth. So what do we mean is like when we talk to some PI, they have generated like petabytes of new data, but they don't have enough people to analyze them. So there's a lot of missing insights over there. And also, when you're a scientist, you have actually a lot of scientists has a lot of interesting hypotheses on their mind, but they can only work on like one idea at a time because they don't have the bandwidth to do this kind of analysis. So because running a lot of these kind of scientific research workflows takes forever for humans, and it also costs a lot. So increasingly we will observe this plot, which is like as time goes by, the demand of scientific expertise, like biomedical expertise, grows exponentially, but the supply of it just like grows linearly with a small k. So there's like a big deficit here that we want to bridge in order to like dramatically increase the speed of scientific and biomedical progress. So this means that we need a new way of scaling expertise. So one way to scale it is just to make new scientists, right? But it's impossible, as we all know. Like it's expense training scientists is expensive, slow, and constrained by education and so on. So we need a new way of scaling. And luckily, we're able to see that LLM agents, AI agent that is able to scale expertise in other domains. So just a very brief overview of what is AI agent is a human make a request to the LLM, and the LLM perform an action to the environment, and then this environment would kind of perform the action and get the result from this performance. And then the result or the observation will be used as feedback to the LLM. And then the LLM will kind of decide if it needs to make more actions or it just stops after it thinks the task is finished. And we're able to see that this expertise is scaled to like coding domains like using cursors, legal domain with Harvey, and there's also many other domains increasingly. So we're thinking, can we extend the same paradigm of the agent to do biomedicine? So we do believe that the future of biology is agentic. So the idea is like we want to create a virtual AI biologist that just automates the day-to-day biomedical research task. So ideally, if we have this AI biologist, it can perform tasks much faster, and they can also tackle many of the tasks at the same time. And also it can suggest and explore novel ideas, novel hypotheses, and we can also move above the text complexity, like moving beyond from day-to-day research tasks, and we can chain everything together. So in the end, we can potentially even automate the entire discovery process from end to end. So yeah, so the key idea here is definitely in the future we're thinking of like augmenting a biologist, just like cursor augment software engineers. We want to build a biologist that have impact of a biologist augmented by AI has the impact of an entire specialist team, and want to make biological research really universally accessible, so anyone on the world can access the top-notch kind of a scientific expertise. So agent as a way of technology transfer, and then also yeah, just amplify and extend the bionic progress. Cool. So hopefully that's a quick kind of motivation why this is exciting. Um, and then this talk will be focused on around how to build such an AI biologist. And I guess we'll show the first um, kind of our first endeavor, try to build one, but it's probably not the last one. It's also pretty initial as well. So in order to build an AI biologist, we first need to understand what is a biologist doing, right? So that we can have the AI to simulate and imitate the biologist. So if we look at how biology research is being done today, it's roughly fall into the kind of two categories. If we look at a very high level, the first one is generating hypothesis, where biologists using it's thinking, reasoning, and also running some analysis. It creates a hypothesis like this gene causes tail loss, for example. And this is through, if you think of this step, it actually also involves many individual tasks and workflows. Then given hypothesis, the next step is like we want to there's a biostatistician could look at all of these different public databases or private databases and then to reason about why this hypothesis is true. It can run a lot of statistical analysis, like computing a lot of p-values, try to validate a hypothesis. Alternatively, a biologist can also run a targeted well experiments. So, for example, in this case, it'll perform a CRISPR knockout on a gene in a mouse, and it will observe, okay, the tail is kind of lost. So this is also a way to validate the hypothesis. So as you see here as well, like validating hypothesis is a high-level kind of a goal, but there's a lot of individual tasks that are involved when you validate a hypothesis. So if we really look at it, very broadly, we think this is a one way to frame biomedical research. So it's a loop of hypothesis generation and hypothesis validation. So once the hypothesis is validated, it will be informed to generate the next hypothesis or refine the next hypothesis. And within this outer loop, in each of the steps, there's a gazillions of individual workflows. These are like, running this analysis, doing this task, and do some reasoning, do some well experiments, and so on. So we call this an inner loop. And given this recipe, we can then naturally derive a recipe for building an AI biologist. We first need to a generalist biomedical agent that can just perform a lot of these individual biomedical research tasks. So the task complexity at this level is relatively simple, and it's not like give me a drug for a disease, right? It's like very specific. I want to do this analysis, that analysis, and it's usually a very modularized kind of task that a scientist will usually perform on a day-to-day. And then given this generalist BAM agent, so we can get all the tasks done, individual tasks done, then we need to build a high-level agentic systems that can orchestrate different agents or different tasks, to chain different tasks together to do generation and to do validations. So we will need a potentially specific agentic systems for hypothesis validation and hypothesis generations. So today's talk, I'll focus on this part, which is like building a generous biomedical agent that can just get tasks done. And then we also have some work on this kind of a more autonomous hypothesis validation and hypothesis generation agent, like agentic systems. But I don't think we have time for that today. But yeah, feel free to check it out on another time. But today I will focus on this Biomni projects. Cool. Maybe before I start, I see there's questions. Oh no, these are all in intros. Uh, cool. So yeah, so family is done by a list of great, amazing people together. Definitely, I want to shout out to Serena, Hanchan, Jerry, and Minta, who is the co-members in this project, who has been spent a lot of time on this project, and also want to acknowledge all my collaborators and also our advisors as well for making this project together. So now we kind of zoom into the individual task level, right? So maybe on the individual task, the granularity is like, I want to do this analysis. I have this question, what is the mechanism of human losing the tail? These very specific, relatively open-ended but specific questions. And then if we look at within this in each individual task, if we zoom in into it, it's basically when a biologist resolves this individual task, it's a loop of reasoning and actions, right? So when this question comes in, I first think about how do I resolve this question with use reasonings. And then I will okay make a plan how to resolve it. And then I will really follow in the steps in the plan, perform experiment, perform analysis, perform these actions, and then get the task done. And then the task output will inform me to if I need to follow the do the next step or if I need to change the step and just get kind of this iterate over this reasoning and actions and like a loop. And we know there's a lot of progress recently in LM reasonings, but we realized that actually the bottleneck for making to simulate this loop is the biomedical action space, which is like undefined. So what we mean by this is like the LM currently cannot is not compatible with all these specialist biomedical actions. So this includes the databases, web experiments, bioinformatics tools, statistical analysis, and so on and so on. So these actions are numerous, diverse, and very specialized. And we don't in another word, it's basically we don't have an environment for biomedical AI agents. So our first endeavor is like, okay, we don't have environment, now let's just build one, right? Then the first question is how do we build a biomedical environment? Because biomedical action space is like super complex, large, and scattered everywhere. And about in biology, there's like numerous subfields of biology where each subfield don't know what the other subfields are doing. So it's like very scattered. And then there's also just a lot of know-hows, a lot of private knowledges that are not documented anywhere on the internet. So the LM has no way to know because it's not in the pre-training corpus. So okay, now the question is, how do we, is there a kind of systematic way to create such action space? So I guess the first part of our method, we're thinking, okay, like how do we systematically do it? And we are inspired by this kind of a literature research agent, where we basically going through the bioarchive. So there's 25 subjects in the bioarchive where they have defined it really nicely. And then in each subject, we can grab 100 recent published papers. And in these papers, you can think of it as a snapshot of the recent research of the subfields of biomedicine. And then given this snapshot with these papers, we have another agent. We call this action discovery agent, where basically it reads through each chunk of the paper. While it's reading, it's basically we ask the agent to say, okay, what tools are needed, what software are needed, what databases are needed to reproduce the result from that paper on that specific snippets. And then we just run them through these 2,500 papers. And then in the end, we get a collective, very large set of tools, software, and databases that are necessary to reproduce the result. So, so we call this as a representative action space of like every biomedical subfields. Yeah. But of course, this action space we get is like massive, right? The one although they're essential to do biomedical research, but because it's also using LM, it's like very noisy, and many of them are also just very specialized, and also many of them are like overlapping with each other. So for the first version, although we have this kind of a North Star, like where this entire space look like, but what we did is we manually going through them, and I mean, after some pre-processing, and then identify the ones that we are familiar with, we have expertise with, and then we implemented them. So this is what we call the Biomni E1, which is the first environment, a single environment with diverse tool, software, and databases. So this is a basically a kind of environment that all of them we manually curated. We actually initially we tried this automatic curation as well, but it just does not work really well. Maybe it's also because when we tried it, it's like Cloud 3.5, so it's probably very nice, much better. But still, like, so we kind of categorized into three parts. The first one is this kind of a softwares. So the softwares, what I mean here is, like this very popular bioinformatics and bioinformatics softwares like in R packages like DSIC2, in Python like ScanPy, BioPython, psychic image, and there's also command line tools like P-Link, Muscle, Homer, BWA, and so on. So I think it's actually very interestingly, it's like this is also the first time I guess a single person can do both Python and R. I know in biomedicine, translating packages is usually like a nightmare. So now you have a single agent that can run both Python and R and even interleave everything with no issues.
Hey, Kevin. This actually seems like the perfect place to ask a
Mm,
couple of questions. We've
yeah,
got one from Jing. I'm going to kick it off with a question of my own.
yeah.
So, first of all, have you talked to the um, protocols.io folks in Berkeley? Have you heard of them?
I know Protocols IO, but I haven't talked to them. But that would be a
Yeah.
great.
So the guy behind it named Lenny, he's been doing this for ages.
Nice.
He would love to see this, and I'll bet you guys would have a fruitful conversation. But
Cool.
my question is, I'm not surprised that your agent really struggled to do this task of find all the actions that a biomedical scientist can take,
Mhm.
because it's equivalent to trying to make a catalog of
Mhm.
every Python library you could use.
Mhm.
Like PyPy is like a dumping ground there,
Mhm.
and no one knows what is good, what is bad, what's
Not.
old. Like there's a million alternatives and duplicates, and no one keeps track of that stuff, right? So my
Mhm.
question is like, don't you think that your AI agents are gonna
Mhm.
somehow have to do what human coders do? We just
Mhm.
use our judgment, we use reputation,
Mhm.
it seems like you're setting yourself up for a very difficult task of cataloging everything, but maybe your approach is really nice for this first step of
Mhm.
handcrafting a core library of
Exactly.
actions that you
Yeah.
can trust, that you've curated. But
Mhm.
how do you acknowledge the ocean of other actions that
Mhm.
are relevant? I guess
Mhm.
that's my question.
Yeah, I think that's a super interesting point. So indeed, we find that when we first using this, oops, like like this procedures, we get a lot of noisy informations. And I think this is basically our denoise version in some sense. Like by denoising, we mean like we as a few
Yeah,
students make the judgment, right?
yeah,
Um, so we also realize that there's just so much junk out there, so it's impossible
yeah,
to just put all this junk into our single framework. So that's why actually in the E2, in the environment 2 version, we are stop using this approach. We're more using this community-driven approach.
yeah.
So people find something useful, we kind of we verify it, and then they can add it to our environment. So this way it's more kind of I guess at least there's some people need it. Uh, yeah.
Raj, what's the name of Cheng Lai Si? Is that the name of the guy?
Changlesi, yeah.
He's a Stanford prof, right?
Uh,
PhD.
Oh, he's a PhD student at Stanford?
Yeah,
yeah, yeah.
that's right.
Yeah,
Are you familiar with him?
yeah, yeah, I'm good friend with
Yeah.
him.
So he's also trying to crowdsource kind of
Mm,
like this tacit knowledge stuff. This seems to be a trend that because I think it's a good direction, obviously. Okay,
yeah.
now we're going to test this new technology. You ready, Jing? I'm going to press this answer live button. Let's see what happens. You should be unmuted. Did it work? Or did I delete the question? Uh-oh. Okay. Raj, help me unmute Jing so that we can bring them to the stage. Dang. Thought we had this solved. All right.
No worries.
Let me click on.
I think it's working. I asked Jing to unmute. Oh,
Oh,
okay.
okay.
Hello.
Hey, Jing. Yeah, we hear you.
Yes, actually, my question is just like in Q&A. So
Hmm.
I want to know how do you manage your team to work together on this bigger project?
I see. Yeah, yeah. I think that's a great point. Um, so I think honestly, our team we kind of evolved in some sense. We initially just few students, and then as I will show later, we have a lot of case studies and different benchmarks as this each individual demands go. We just find the right people and then just grab them into it. But honestly, It's like very kind of a demand centric. So for these kind of people, they don't involve in everything. It's just that very specific task. So I think that's how we operate. So we have like there's three very core people who are working on it every day, like setting up the infrastructure and everything. And then we have this kind of star like kind of just grabbing the different people to get their expertise and then put that in the co-authors. So yeah, I would say in the core it's actually a very small number of people. So there's not much kind of management in some sense. It's just more like people working with each other and having fun. Yeah.
All right. Now you can dive back into the talk. Thanks.
Sounds good. Great. Yeah, I like these questions. So yeah, so basically we divide into so the software here, as I mentioned, and then we also have the databases. So because as you probably all know, the biomedical databases are like so important. It's basically the past snapshot of every possible experiments have done before, and also the knowledges that people have curated. And when we make discoveries, usually rely on these past knowledges to make the new ones, right? And we cover two categories of databases. The first ones are these massive public databases with web API. So this include like Open Target Genetics, Nomad, Cell by Gene, ClinVar, um, yeah, AlphaFoldDB. And so for that, we use a database sub-agent kind of thing, just to takes in natural language, and the sub-agent would takes the web API kind of schemas and write some basic code and get you the answer. So this is like much more flexible compared to defining functions for each databases. And then we also have a data lakes. With data lakes are the files that does not have any kind of a web API existed out there. So these are kind of raw data set, like data frames with columns and rows. And for that, we just put it in our data lakes and we let the agent know that you have access to that data lakes. So the software and databases actually can actually cover a wide range of different tasks, and these are the kind of core essential part of the environment because this is the most general ones. But we also realize that for a lot of corner cases or like tasks that we require very specialist knowledges, the LLM actually cannot do not know this kind of stuff. So for that, we create specialist tools. So these include like web lab tools like Golden Gate cloning, oligo assembly. These are like protocols. So for these protocols, we basically get it from some top lab at Stanford, steal their lab protocols and put it in our framework. And then also there's like AI models like DiffDog. We also have recently we have AlphaFold, this kind of stuff. That when you ask LLM to create on its own, it can be potentially kind of time consuming and difficult. So here we just create a specialist tool for that. So the LLM does not need to create its own its own code. Yeah. So here we define specialist tool if it's private knowledge or if it requires the LLM to write a lot of line of code, or the LLM cannot write code for that. Cool. So given this environment, we then build an agent that can utilize this environment really well. So when we design the agent, we have this philosophy like, just don't put too much constraint on it. Before Biomni, there's also several kind of biology agent work, but they are all like very specialist agent. They focus on specific applications. Like they define the precise workflows. Like after this happens, you should do this. After that happens, you should do that. Our goal is to become a general purpose biomedical agent. It can do all kinds of different tasks. So it's kind of impossible to define workflow for each one of these tasks. As also you will realize that biomedical tasks are like really fluid. It's not like it's always following some templates. It's really flexible. So given that, we kind of design an agent just to make it very general purpose, very flexible, not much structures. Um, yeah, so the first step is retrieval because our environment is like massive environment. You don't want to dump everything into the context because it's really wasteful. So given input questions, basically we will do the retrieval to retrieve a subset of tools and software and the databases that are necessary to be used for these questions. And then this so we try various different kind of retrieval methods, like embedding-based RAG approach. And in the end, we use this retrieval agent, like sub-agent approach, where it's like another LLM just read through the description of its tools and of its databases and generate, and also takes in the questions and use reasonings to identify the tool software and databases. So we find that is usually much, much better and much more flexible as well, because in embedding-based RAG approach, you will need to define the pre-specified K, which is number of tools. But here, using the LLM-based approach, you don't need to specify the K. You can just be very flexible. Cool. So after it's retrieving the resources necessary, it will perform reasonings. So the reasoning here is basically the steps it took to answer these questions. So we rely on LLM to come up with this plan. So instead of a pre-specified workflow template, the LLM actually has seen a lot of stuff. It has seen a lot of papers, literature, forums. So it knows a lot of how to perform tasks in an average fashion, in average balance fashion. And then this plan will also be tracked along the entire process with we call it adaptive replanning. Because as I mentioned, like once you sometimes when a step failed, a human scientist will reason about it and update the plan or fix the steps. So we need this kind of adaptive replanning to make sure this is working. And lastly, we have the actions. So if given each step, how do we get this step done? And we're inspired by this framework called code as actions, because code is a very general way of task solving. And code is also perfect for our environment because our environment has a lot of softwares and databases where there's no kind of pre-specified functions. It's just like we give the LM, you have access to this software, you have access to these databases, right? So there's no pre-specified functions for this. And then we let the agent to just, the code allow the agent to use this software database and pre-specified tools very intelligently. And the code, another benefit is it also compose more complex logic. Because for example, now you can do for loop, you can now do min and max, just more complex logics that can be used for that. So this is the overall overview. So it's actually a very simplistic agent architecture. We actually experiment with many other more complex one, but in the end, we just find that this is actually the simplest, works the most robust and flexible. Basically, you're given task, we had a retrieval, we'll do the reasoning, we'll do the tool use by coding, and then we'll do the execution. So we have a sandbox and we'll run the code and get the feedback from the sandbox. And then we'll do the next step reasoning and then so on and so on until it gets the answer. Cool. So so that's kind of the method. Maybe I can stop for a while just to see if there's questions.
Yeah, we've got a few questions rolling in. Take a quick, can you see them in the QA, Kexin?
I don't see.
I think
go.
I think that one that might be relevant for now is Kratina's question, which is about the biomedical action space. We're going to do a test. Oh, thanks, Raj. So let's see if Kratina is unmuted already. I'm going to see if this
Hello,
system.
can you hear me?
Yeah, perfect.
Okay, great. Yeah, I was wondering, it's really cool that you defined this biomedical action space, and I'm wondering what the histogram of action frequency looks like. So maybe you chose your set of actions because there's some small number of actions that represents the vast majority of actions found within the space.
Yeah, so I would say indeed concretely speaking, our action is actually a piece of code, right? And then it interleaves the software databases and the specialist tools. And so in that sense, it's highly dependent on like I also mostly sized by the software and the databases. Because for the specialist tool, for each subfields, we currently only define 5 tools that are really popular. It's mostly defined by the software and databases because we run analysis, we run a trajectory analysis and to see what kind of resources it is mostly used from Biomni E1. It's actually the databases tools and then the softwares. And for the specialist tool, it's mostly very kind of it's only be used for very specific tasks. For example, like web app cloning protocol design, then you will need to use some specialist tools. But for majority of time, it's just I'm writing a lot of code, writing a lot of from the database queries to get task done, which is also how I guess real world biologists, they most of the time just searching stuff, using some literature research tools, and then to do things.
I
So,
think there's an implicit question in the question, which is
mm,
imagine you kept on going, cataloging, these the action space.
mm,
The intuition is that there's probably some kind of like really skewed distribution of tools that get the job done.
yeah,
That you don't have to boil the ocean. There's actually a pretty small number of, core techniques, core resources,
mm,
certainly within a field or a subfield of biology that get most of the work done,
that's
which
it.
I think is a really good point. It's a really good insight. It makes your job a lot easier.
Yeah, actually, yeah, I think that's really, that's actually correct, right? Because, for example, like ScanPy, it's like it covers all the single cell analysis. There's actually gazillions of other software packages for single cell analysis as well. But because ScanPy is like so popular and so useful, we just need to include this. So we don't need to define all the other actions. We just need to give the LM you have access to the ScanPy packages, and
Yeah.
it just unlocks such a wide range of different actions. Um,
Kexin, I'm seeing another question from Nikhil Kandikar, which I think is also like good for this moment.
mm.
But the question is, can you talk a bit about context management when you're doing these tool callings over multiple steps? Are you going to address that later? Or do you want to dive into that level of detail now?
Yeah, I can talk about it now since I would.
Okay, I'm going to bring Nikhil to the stage. Nikhil, if you want to add any color, go ahead. Also, Kexin, you can just jump in and start answering.
Okay, sounds good, sounds good. Yeah, I think I understand the question. So actually, when we design agent architecture, our design principle is like we want everything, the main information is everything is in a context. So there's no kind of breaking.
So
And
it's
then
just one big ass prompt.
yeah, one big ass prompt, just
It's
for the
not some complex like workflow of parallel processing, right?
yeah.
Yeah, I
Uh,
love that. Keep it simple. Make it complex if you have to.
Exactly. But we do have a sub-agent design. So basically, we find a lot of tasks that we can allocate it to another agent, and
Mm,
it's like very standalone. So actually, whatever happens in that sub-agent does not influence the main information flow. We just have that as a sub-agent. So by sub-agent, for example, actually the retrieval is a sub-agent. And we have some database queries. These are also sub-agents. For example, database query, you don't want to store all this database schema into the main information flow, right? Because it's just not useful. Um, so I think we try to identify these standalone tasks, and then we
yep.
put these as sub-agents. And the main information flow is just the essential kind of tasks and code that
And then Nikhil actually had a good follow-up question. Nikhil, are you unmuted? Do you want to ask it?
Yeah, I'm unmuted. Yeah, I was just gonna ask like how do you ensure do you ever run in the case where like it's like unable to like decompose the task properly and like it just gets like stuck in the loop or it
yeah.
starts writing code but it's like not compiling and it doesn't know how to like self-correct like in those cases like how how does the user like help the agent like self-correct and like how do you ensure like
Mm.
reliability over like long-term tasks?
hmm Yeah, I think that's a great point. So I think for like so honestly, this very depends on the underlying LLM capabilities.
Mhm.
Um, so what we observe is like for tasks that is very representative on the internet, it's like very common. It's able to do it pretty well because it has seen gazillions of examples. But
Mm,
for tasks that are like not that representative, LLM actually sucks at it. So right, but
yeah.
there's a ways to alleviate that, right? So, I mean, one way is of course the next generation of LM, because I don't know, all this frontier AI lab is trying to collect all of these traces from biologists, so it will potentially get better.
Mm.
Um, but just for now, you can actually also learn from these biology expert and then just to grab their, just squeeze out their brains, right? And then just get like a list of uh, steps that they will perform for this expert level tasks. And yeah, actually, in our we have experimented that for some of the tasks, and it's actually performing like much better. It's basically like future examples. It's able to follow the guidelines and then have these kind of expert level behaviors for that. And for reliability, indeed, like, coding is actually not that reliable, right? Because it's, for example, especially for biologists, they don't know how to code, so it's very hard for them to understand. So that's why we try to want to alleviate that. The first way is like we have a guardrail system that always try to detect the hallucinations in the code. And the second way is that we actually, for each code, I mean, in the web portal that I'll show later, we have a natural language explanation of the code. So this way biologists can also understand it. Yeah, but there's also, I guess it's these are all like measurements that can help alleviate, but it's also just not, I think reliability on its own is like a huge topic. There's also other ways to make sure it's more reliable. Yeah.
Kexin, we're coming up on 15 minutes left. How many more slides do you have?
Oh shit. Okay. I have
Maybe we should rumble on.
okay. Um, cool. And now I'll quickly delve into the result. So first using some like exam style benchmarks. So they are like we use 45 questions from these two DBQA and sequence QA from Feature House for tune the prompt. And then we're able to see that we're able to get a human level performance on DBQA and the sequence QA. But of course, we kind of it's kind of a sanity check, right? Because we kind of tuned the agent slightly. Um, so we tested on a completely unseen development set, zero tuning, just complete like one shot generalization. We actually only tried it once, so without any tuning. So this is the performance that we got. It's like actually pretty robust compared to LM. It has like three-fold better because LM is actually what biologists are using right now, right? So Biomni, if you're using the same task, you can get three-folds better. But still, that's still not enough, right? Because that's exam style questions. And in the real world day-to-day research, biologists are not taking exams, right? They're doing like real biological research tasks. And for that, we curate a new benchmark spanning across eight different tasks where we have some ground truths that we can compute. It's like a proxy of the ground truths that we can compute how good is this agent. And for example, like GWAS collagen detection, perturbation screen design, single stylistic annotations, disease text analysis, repurposing, rare disease diagnosis, and so on and so on. So overall, we're able to see that Biomni has better performance than all these baselines, better than a coding agent, better than an ablation. It's like React, which is a ablation of Biomni without using coding, but using like function calling to perform the actions. And we're able to see that it has better performance than LM by 400%, by coding agent in average by around like 40%. And the ablation for React is better than on average like 10%. And then we're still not satisfied by that, because there's still like benchmarks and some proxies. We really need biologists to really use them. So we work with a series of biologists and to really ask them, giving you this tool, how do you want to use it? And then, so we're first working with Le Cong's lab. So Le Cong is a CRISPR pioneer working on his lab. They work a lot on wild experiments. And part of wild experiments, one of the fundamental wild experiment task is the cloning. And for one of the scientists asked Biomni this question, this plasmid sequence, blah blah blah. I hope to clone a guiRNA targeting human B2M gene into this plasmid. Yeah, could you give me a final map of the plasmid and also step-by-step guidance? It's like a protocol for the wild experiments. And the Biomni basically takes this question, it runs the plasmid analysis, it runs the guiRNA design, it runs the oligo design, and so on and so on, and it generates a plasmid map in the end. And we're able to see that this wild lab cloning protocols is like very granular. It has all this sequence informations that is actually generated from other tools in Biomni. guiRNA design tool, for example. And in the end, a scientist will follow the protocols to perform the cloning, and we're able to see that the cloning is successful, and you can see the sequence is also aligned. So Jerry here is very happy because cloning takes years of training, and even then, they spend hours navigating tools like snapgene, edging, primer blast just to design one construct. So now Biomni can just automate it in 10 minutes. And then further following up on this wild experiment part, we did around 10 open-ended tasks for cloning. So these are like very diverse tasks that are real world and Jerry encountered in his research. And we then recruit a trainee who is a master level Stanford student who just graduated, but will start a PhD student, will become a PhD student in a year. And then she actually has done web cloning before, but she is definitely not an expert. And then we also have an expert who has done cloning for the past 8 years. So like really world-class expert at Stanford. And then so for these 10 tasks, we just asked LLM, Biomni, and Trini, an expert to perform this task. And then we shuffle them, and then we let Jerry to grade them blindly, which one is which one has the highest, which one is the most accurate. Sorry, how accurate is the result, and how complete is the result, and so on. And in the end, we aggregated them. We find that Biomni has similar accuracy as expert, and much better than trainees, and also, of course, much better than the LM. So we're able to I think this gap is really interesting, right? Because here now we're saying the AI agent could be an interesting education tool that can democratize all this expertise to anywhere, to anyone. So in the future, a trainee does not need to bug the, I don't know, 50 PhD student to ask questions. You just need to ask Biomni the questions. So that's the wild experiment part. We also know a big application is on the dry lab part, because there's a lot of data analysis that takes forever for bioinformatician, for scientists to do. For example, this is an example. We work with Michael Snyder's lab, where they have a lot of wearable sensor data. So here, as an example, is the continuous glucose monitoring data. So our agent basically takes in this 458 raw Excel sheets, and we ask it to to explore the data set, process it, and generate some meaningful hypothesis around this data sets. So we're able to see that Biomni goes into it, conduct a lot of different steps, generate a lot of visualizations, and in the end, generate some interesting conclusions. And interestingly, we find that Minta, when she does the same task, it costs her 3 weeks, with each day 2 to 3 hours to do it. And it got similar conclusions. And Biomedical does it in 35 minutes. So this is a dramatic kind of a productivity increase for biomedical scientists. And I think this also hints at the more complex is the data, it's probably where the agent shines the most, because it's just the massive data set is just not suitable for human scientists to do. And then so variable center data actually does not require very, very deep specialist tools, because it's basically Excel sheets, manipulations, running some data analysis, and etc. So we also tested on a dry lab analysis that require a lot of domain expertise. So that's the multi-omics data analysis. So Han Chen here is an expert in single cell analysis. So he was very interested in this new data set from a Nature paper, and it's got kind of a 300K single cell RNA-seq and single cell TAC-seq data sets. And then Han Chen basically created a very long, detailed prompt on how he wants to analyze this data. So Biomni basically follows the instructions, use all these different tools, different softwares, different specialist tools, and generate some interesting figures, visualizations, and also hypotheses. So actually, these are like novel hypotheses that are not covered on the original paper. So like novel transcription factors, this gene showed high vector activities across skeletal lineages. So these are like testable, actionable hypotheses that maybe scientists, they can really follow up with doing some more in-depth experiments. So cool. Yeah, so this is like 3 case studies that we demonstrate. But after that, we really want to have fun and then try kind of ask various different kind of questions that a typical biological scientist would encounter. So which we were able to see that Biomni can get these tasks done at some level for almost all of these tasks. For example, variant interpretation, like for human geneticists, this is such a fundamental task. For ADME profiling, this is like for drug developers when you want to predict the distribution or metabolism or toxicity of a drug. This requires using some AI tools to predict these models or to predict these endpoints. And even the most tedious task is downloading some biology data set. It takes biologists, at least a few hours to do it, but now agent can get done in like 5 minutes. And then CRISPR screen design, cloning protocol design, as I mentioned, and there's also some application on diagnosis for clinicians. And there's also like complex data analysis on perturb-seq data, and also like molecular docking. There's like very expensive computational experiments. And there's also the single-cell RNA-seq annotation, which is a fundamental task that takes scientists often like months or even like years. Now Biomni can give an initial kind of annotations for the scientists.
Hey, Kexin, we're at 5 minutes. I want to make sure to leave room for questions. Any last big points you want to make, or should we just dive into questions?
Yeah. Maybe one last quick point. We have this free web platform. People can try it out. It's called Biomedical. I probably don't have time to do the live demo today, but it's
No,
basically
I can actually, a lot of people in the room have been trying your tool. We can see in
okay.
the comments and
Sounds
in the
good.
questions. So
Nice,
you've got a warm crowd who's actually very
Mhm.
familiar with this.
Nice, great.
All right, let's dive into the questions, folks.
Mhm.
I'm going to kick it off with a provocative question.
Nice.
So, you show a lot of results where an LLM is the baseline, but that's not the relevant baseline, is it? The relevant baseline is just using Claude Code. Like
Mhm.
everything I've seen so far, you could probably make a kind of bad version of this just with a claude.md file. Have you been trying
Mhm.
that as a baseline? Because I feel like that's the thing to test, right?
Mhm. Yeah, I think that's a great point. So the coding agent is basically, I mean, like it's not like the cloud code version, but it's like a basic coding agent.
Yeah.
And cloud code intrinsically is also React plus coding agent. Although it has more complex stuff. Yeah, and then we are certainly interested in trying it out as well. But I would say the difference here is the environment, right? Because the environment that gives the access of the LM to the scan pipe packages, all this p-link and all this stuff. And there's also these specialist databases and stuff like that. So if you directly try the cloud code, it does not have access to these kind of stuff, then it will not perform super well. I'm assuming, but
But I mean,
it's
all of those can be captured in a GitHub repo, presumably, right? It's all code. And so, I think like the challenge is how far can you get just using off-the-shelf Claude Code or Cursor,
yeah.
where a lot of the work you've done here is captured essentially in a specialist library that it accesses. So
Mhm.
that's I think the challenge. I don't know if you guys are building a business or intend to build a business around Biomni. But if you do, that's going to be a challenge you should like take head on. Just
Yeah, definitely. So I think
I'm trying to be provocative and interesting.
yeah. I think actually, now that I think about it, it's actually so Cloud Code. The difference between Biomedical and Cloud Code is basically the A1 architecture, the agent architecture. So the environment we can still combine with the Cloud Code, right?
Yeah, totally.
So I think the value that honestly, what we're creating is mostly the environment,
Exactly.
instead
Exactly.
of
Which
the
is why I'm thinking like you should take advantage of
mm,
one of the best capitalized, agent tools out there.
that's the
Just ride that wave. Like
mm,
it should get
yeah,
better and better without you having to build all that stuff, which is amazing. Okay,
yeah,
first question is going to come from Yujia Zhang.
mm,
I'm going to click on the button and you should be able to ask about reinforcement learning. Can you unmute yourself, Yujia?
Hi, very awesome presentation. And because you mentioned a lot of like agent and environment and action space, I'm
mm,
just curious, is this related reinforcement learning or you
yeah.
just use these terms?
Yeah, it's definitely related to reinforcement learning. We're actually training a Biome IL agent right now. Uh,
Mhm.
so yeah, we can yeah. So I mean, the original motivation is also inspired by the
Oh,
art.
interesting. What is that agent what part of the workflow does it handle?
Yeah, so it's basically all of the these tasks. So we're because we see that here it's actually far away from human level performance.
Yeah.
So we try to want to see if RL can improve on these
On those specific tasks.
on specific tasks.
Cool.
Is that human in the loop to provide any feedback or not?
Currently, no. Currently, it's just the quant choose as a reward. Yeah.
Okay, yeah. And I have another question, and is that you mentioned the kind of embedding-based RAG fields often. I want to ask you more details about that and why you choose the LM as a retrieval tool, as I remember correctly, you mentioned.
Yeah.
Yeah.
Because I think like as a scientist, when you have a new question and you have all of these different tools and
Yes.
environment, you actually require some reasonings to kind of select which tools to do. If you do like simple RAG-based embedding approach, which is like similarity search, sometimes it's just not granular enough to identify the correct tools. So that's why we find that using LLM as a sub-agent, it actually has the best result. And I think it's also a common, I think, agentic design patterns, like agentic search, that is like getting more and more popular. It's like using agentic search instead of RAG.
Okay, using agentic search. Okay, good to know that. Yeah, thank you.
We've got another question from Shantanu. Hope you're still here. Great question about ChemCrow and co-scientist. You there, Shantanu?
Yeah, I see. So I think these are honestly we are more like yeah, we can of course using this like agent to agent kind of a design, right? So we can also maybe call ChemCrow and call co-scientists to generate hypothesis from co-scientists and done some chemistry stuff. Yeah, so I think that would be a cool stuff. Yeah, I mean, and then we'll definitely want to integrate with the web lab infrastructure as well. But I guess the challenge here right now is like it's very hard to create the APIs for the web lab, something like a programming language to very flexibly orchestrate different web experiments. I think that's a very open question, and yeah.
We got a question from Sanat Mishra about the rate limit. Seems like someone who's been using your tool and is curious how you're handling rate limiting.
Yeah, so currently I think each user can do 550 questions per week on the web platform, and on open source, of course, you can do it, how many questions you want. Yeah.
Okay, we have a few more questions. Before we jump into them, we have a tradition in this community of doing the big screenshot. So can you stop sharing, Kexin?
Yeah.
And everyone, if you're comfortable, put your video on, and I'm just going to grab a screenshot. It's like a little artifact of our community. And I'll do a countdown of 5, and you can wave. 5, 4, 3, 2. Oh, wait, there's still still people hiding. Okay. 5, 4, 3, 2, 1. Got it. Thank you. Okay.
Thanks.
We got a bunch of questions about MCP from Kevin. Oh, they're all from Kevin. Kevin, I'm bringing you to the stage. You want to ask about MCPs? Well, if Kevin can unmute himself, the question is basically, are you using MCPs? Are you using the Model Context Protocol kind of framework at all?
Yeah, so actually because so we're thinking about multiple ways to use it. Like for one direction is like we use some existing MCP tools into Biomni, and we're supporting from open source community. They have contributed a framework trying to add these MCP kind of servers. And another way is like using Biomni as an MCP to the other stuff. Yeah, I think we also kind of try to support that as well. Yeah.
Kexin, we've also got a few questions from folks wanting to actually collaborate with you. Maybe we can answer that all at once by you providing